All right, welcome. Starting with a question about faceting and smooth. So here I'm just starting with the Lego sets data set again, putting pieces on the x-axis and US retail price, and right. And so typically we would want to do G on points, right? So one question was, what's the deal with faceting? So if we look at the Lego sets, I think it was category, right? I think a couple things we could do. We could say we want to color the points based upon category. I think that's the name of the variable, right? Okay, great. However, particularly with the Lego sets, because there's a lot of observations here, the last thing that's drawn, which is normal, kind of overwhelms. So what faceting allows us to do, so we could do facet wrap, and you have to do this tilde. Oops, just switched windows on me. So you have to do this tilde thing. We will talk about that, I think, in the next week or two. This is like R's formula syntax. So I could do category, and I can actually have a faceting um and color, right? So you can kind of see how the relationship is. So what faceting is doing is creating a separate scatter plot for each of the categories. Does that answer your question, Togi? Was that or do you
Yeah, yes, Professor.
Okay. So then the second thing, so if I take this bit, right, we go back to our scatter plot, there's something called geom smooth. Now, oh, well, let me get rid of the color because that's gonna mess things up. And it's gonna draw this. What in this case, it is um doing what's called a generative additive model. But I tend to prefer, even though it's a little less performant on large data sets, lowest regression line. So this is what's called a localized regression. I'm actually going to talk about this. Actually, I really technically won't talk about it until next semester. But since you're asking, I think I can do. Um, I could point you to a page here. So if we go lowest regression. So what lowest regression does is it's just doing like a lot of localized regressions as you go from left to right. So I have this little shiny application. So if this is our scatter plot, it's estimating a regression. So here we're trying to figure out what's the predicted value at -1. So it's going to say, well, give me points near -1, and it's going to just do sort of technically it does a quadratic regression, but we could think of it as a linear. And the shaded colors here, the lighter means the less those values count in the regression to the point where you get to these white points, which aren't being used at all to estimate this. And so the smooth geom smooth is this. That's what this is doing. You're just kind of moving from left to right, and so when we get in the middle, somewhere in the middle, right? We could see we're not using any points over at -1 or any points over here. We're the points really close to zero, we're using a lot, and then we kind of weight them a little bit less as we get further away. So that's what geom smooth is going to do. This is a topic for IS 382 when we get to regression and the like. So, but I think in R, this is kind of useful to kind of see. I use this frequently because I could say, oh, it looks like there's a linear relationship between pieces and US retail price until you get to about 6,000. And then this happens. But that's sort of a function of, I think that's largely a function of there being fewer observations. And soon we're going to talk about a little bit more about transformation. So this is a case where we could do a scale X, a log transformation, and I would probably do it on both um, the X and Y axis in this case. And now the smooth should be, well, it's a little bit more quadratic because we have a lot here at the lower end. Okay, go ahead, Toki.
Professor, so what's the difference between the GM smooth method equal LM and the Loises?
Oh,
Lois?
Lois. Yeah, that's pronounced Lois. So if we do LM, that's gonna do just a linear regression. So the method is what kind of regression are we going to use? So LM's is short for linear modeling. That is a topic we'll go into great detail in 382. It's sort of the first meaty topic in the second course. So there's a whole bunch of methods that you could use. Turns out, right, so if you do question mark LM, it's a function in R to do linear models. So if you don't specify anything, it's going to probably do Lois. So
Can I ask you one more question,
yeah, of
Professor?
course.
So, some, like when I was doing the lab four, some of the example that from the, I think, chapter nine or chapter one was like, sometimes we were adding the colors in geom point, and sometimes we were adding the color or the shape in the aesthetics. So, do you have, so like, could you, tell me when is the right time to use the color or the shape in geom point, and when is the best time to use it on the aesthetics?
Okay, so if you put it in the aesthetics, you're mapping it to a variable in your data frame. So you want the color to be defined by a variable in your data. If the answer to that question is yes, then you put it in the AES function, the aesthetics function. If you just want to change the color or the shape, then you put it outside the aesthetics, and then it'll just be a constant. So, for example, so if I right, let's look at it. Let me do this. So I could say if I say color equals category, right? That's going to color each point. I can probably get rid of the smooth here. So it looks a little bit better, right? That's going to color each point by category versus if I could put color, I'm sorry, oops, equals blue, for example. Now, just every color is blue. The blue doesn't mean anything other than, I mean, it doesn't have any meaning in terms of the data. So if it means something in terms of data, put it in the aesthetics. If you just want to change the color, just put it out in the geom point or whatever you're doing.
Thank you, Professor.
Yeah. So the AAS is specifically about mapping your data frame to features on the plot. Now, so and you could also do what is it? It's shape, right? And I could say so. There's two is triangles. You could Google. There's a whole bunch of them. Now, sometimes so you can do both. So up here, I can if I add shape equals category, right? So now you could see we have the color and shape is different for each category. This is something I actually do. This is actually good practice to have things represent it multiple ways because if somebody is colorblind, for example, they could still potentially differentiate the points by the shape, or if you print it black and white. So as a principle, might be a good idea to do both. Although this is a bad example because normal is so dominant is the dominant category in this data frame that it's you can't really see anything else, which is why on an it's situation like this, going to the faceting might be more appropriate because then you could quickly see, oh, there's almost no books, few collections, extended a little bit. Gear is actually completely absent here. So, um, I hope that helps.
Can I ask you one last question?
Yeah, no, of course, please.
The one question is, Professor, sometimes I get confused about for what to put in the X and what to put in the Y, just based on looking at the text.
Oh, you mean in the lab?
Yes.
Um, yeah, I don't know. I can't remember off the top of my head the questions. So, um, as we get going, it probably will be a bit more clear. Typically, we like if we're doing scatter plots, it's going to become a little bit more clear. A lot of times we usually put the independent variable on the x axis and our dependent variable on the y axis. Terms I really haven't used yet are defined. So the way to think about it is here, I'm trying to predict retail price from pieces, right? That's the way I'm thinking about the relationship. But I could do it the other way. Like I could say, give me the US retail price and I'm going to predict how many pieces the set has. So there there's no hard and fast rule. It really has more to do with how are you phrasing the question. So if you're trying to phrase it as I'm trying to predict this from this, then whatever you're trying to predict, we by convention put it on the y-axis. But they can be reversed. So no hard and fast rule.
Yeah, thank you so much for all the answers, Professor.
Yeah, of course. That's what I'm here for. All right. So, for everyone else and for Doki, I'm glad you're here. Thank you. We're going to talk about reshaping data, um, a little bit. So, and then a little bit of descriptive stats. So, I want to kind of dig into that a little bit more detail. So, this is a figure from the R for Data Science book. I think this is a fantastic way of thinking about what data scientists do. So tonight we're going to kind of focus in a little bit on this tidying. The lab three was supposed to be on importing. I'll talk about that maybe next week or the week after. Um, and particularly when you're going to do your data project, if you need help, we can get into that. There's just a whole bunch of different ways you can import. But we're going to talk about tidying and maybe a little bit of transformation. We did visualization last week. And then the rest of the semester, we're going to start getting into modeling, and certainly 382 is a lot of modeling. Communicate, I kind of think of the R Markdown as sort of my way of getting you to think about communication. It kind of gives you a way of combining code and your descriptions and your explanations of things. So communication's always there, and that's kind of an important part. We'll talk more about, sort of in terms of this course, thinking about communication is going to be like in your data project where you're going to analyze something of your choosing. Okay. But like this gray box, right? That's where we want to spend a lot of our time. And it's going to be an iterative process as we try to understand our data, understand the world, or whatever we're kind of interested in. Now, to begin, right, for pretty much everything we're going to do in terms of modeling. So we're going to do inferential statistics in this course and predictive modeling in the next course. All of these statistical methods require data to be in what Hadley kind of termed the tidy data, but it's sort of this structure where each row corresponds to whatever we're interested in, right? So I do a lot of educational research. So I look at a lot of data frames where each row corresponds to a student. And then each column represents some kind of information or measurement for that student. So I could have like name and EMPL ID, and then I could have sex, and then I could also have like, you could think of a grade book, right? So that each assignment could be a column, right? That's a variable or a measurement of some kind. The Lego sets, right? The Lego sets data set. Each row represents a Lego set, and then we have columns like price and pieces and minifigs, et cetera, et cetera. So it's pretty critical that we get data into like this kind of tidy format. Now, within those data frames, we're going to work with two kinds of data. Numerical data, which we're going to kind of refer to as quantitative data, and categorical data that we refer to as qualitative, right? That's sort of the more technical term. So numeric is probably what you think, continuous, like age would be kind of a numeric, height, weight, those kinds of things. GPA, that would be a continuous. And then we could have discrete variables. So those are things that are kind of like counting data, right? If we're counting things, that might be a little bit more discrete. Here's an example, right? So, so if we have an octopus, if we count how many legs or how many legs does an animal have or how many spots, that would be discrete because it only takes whole numbers, where continuous things are, values that can have fractional things. And then we have categorical data, right? So we have regular categories like sex, ethnicity, Lego set category, right? Those kinds of things. But then we can also have ordinal variables, and those are ones that have sort of order, but the, intervals might not necessarily be the same. So the classic example is Likert response data. So you took that survey and you responded on a scale where you have strongly disagree, disagree, neutral, agree, strongly agree. And we could represent that numerically, right? We could say 0 is strongly disagree, 1 is, But that's generally not a good idea because when people respond to likert response data, sort of the weight that goes to each of them, is not the same. In other words, when I go, I'll say, speak for myself. When I go to a survey and say I get a survey question that says, I like statistics. Okay. Well, I'm not neutral about that. I kind of agree. I agree. I like statistics. Takes a little bit like, yeah, but then to say I strongly agree that I like statistics, well, I don't know. That's a lot more. So because of that, going from neutral to agree, that interval might be considered smaller than going from agree to strongly agree. That's kind of bigger. So that's why we would treat that as an ordinal variable. So this graphic here, which is a lot, I admit, but it's a way of trying to summarize in one slide the data types in R. So R has 5 primitive types, all of which are vectors, meaning they have length, right? So the primitive type in R is vector. So if you've done another programming language, the primitives just tend to be constants. And then if you want to collect them, you put them in maybe an array or some other kind of element. But in R, the primitives are vectors, which makes it ideal for statistics because we're generally always doing operations on vectors or matrices. All right. And so the way I have this organized in such a way, so we have characters, which are just any string that you have. You have complex numbers. So that's the square
I
root of
think
-1 equal
probably I
I.
have received a call from this number as well.
Oh, Togi, you have a question? Oh, sorry. Okay. So square root of -1 equals I. We're not going to work with complex numbers, but it is a proper type in R. We have numeric, which is any kind of number value, fractional or otherwise, integers, and then logical, so true, false. So if I have a logical, I could represent it as an integer, right? I could in R, if I do that conversion, it's going to convert true to 1 and false to 0. But I can't always take an integer and represent it as a logical without losing fidelity. So, what does 3 become, right? If I go to logical, right? So there's some fidelity loss. Integers can be represented as numeric, right? No problem. But sometimes numeric can't be represented. So if I take pi, 3.14, whatever, et cetera, and I say, make it an integer, it's just going to become 3. It's going to lose all of the fractional parts, right? Complex character, right? So everything can be complex, but as you go down, if you try to make it that type, you may lose fidelity. So that's why this is represented. Each of these vectors has 2 useful functions. The as dot type is going to try to convert whatever you're giving it to that type. And then R is going to do its best, but you should always check to make sure it converts in the way that you think it should happen. And then it is dot, which returns true or false of whether or not that vector is of that type. Okay, a few other little bits. We have dates, which are technically integer vectors, but they just simply store the number of days since January 1st, 1970. So there is an as dot date, but there is no is dot date. Don't know why, but that's the case. And similar factors, so if you want to represent categorical things, they're technically under the hood stored as integer vectors with this levels, right? So what R does behind the scenes in order to save space, it says, okay, 1 equals adventure, 2 equals, Star Wars or whatever the category is if we're talking about that. Data frame is what we're going to use the most. Data frames are technically just a collection of vectors, right? So that they line up to look like a table. And then we have lists that we'll use from time to time. When we get there, I'll explain it. But a list can just contain anything, right? Which is kind of useful, including other lists. So you can have sort of a nested structure. If you find yourself working with like JSON files, those often come into R as sort of lists or nested lists. Now, this is a pretty early. This is almost like a table of contents for the course. So what we have is our different data types, and then we have our descriptives. So tonight we're going to talk about mean, median, mode, standard deviation, or quotient range. We talked about some of the visualizations last week, but so we have sort of single variables, and then as we go through the course, we're going to talk about, well, what if we have two quantitative, two qualitative variables? What are we going to do? One quantitative, one qualitative. So a lot of this is like summarizing what we're going to do for the semester. So at some point at the end, you might come back and say, well, I have a discrete variable. what should I report for descriptives? You can do contingency table, and then you would use a bar plot, maybe. Okay, so this is kind of that reference. All right, so before we get into sort of the data manipulation stuff in R, I want to talk about sort of a core, the sort of the core descriptive stats that is going to be the foundation for a lot of what we're doing. So if we think about statistics, we're often interested in some measure of the center and some measure of spread. Okay. So center is generally pretty easy to understand, right? We have two options that we're going to typically use. The mean, right? Which is we're going to just take all the values, sum them up, and divide by the number of observations. And that gives us like the middle point, right? So here's our formula for the mean. We're just adding all the values and dividing by how many we have. Okay. Average, probably have used it before. Median is going to take all the values. What we're going to do is put them in order, and we're just going to find the middle point. Okay. And we'll talk about that. Now, when we talk about spread related to mean, what we're often going to work with is what's called the variance, right? And then the standard deviation, which is simply the square root of the variance. But let's dig into the variance, which is this formula here. And in particular, I'm going to start with the population variance, okay, which means we're going to divide by n. I'll at the end say what happens when we have a sample. Now, one of the principles in statistics that we do quite a lot is squaring things. So we can see here, we're going to take each observation, that's what x sub I stands for. We're going to take each observation and subtract the mean and then square it. So squaring has two important properties. One, it makes all of the values positive. Because if we didn't square it, the variance would just be zero essentially in most instances, right? If we're subtracting, because if the value is above the mean, right, we would get a positive value. If the value is below the mean, we would get a negative value, and so we would, have usually roughly the same number of positive and negative values, and that wouldn't be great. So squaring it just makes everything positive. So now we ensure the variance is going to be positive and not zero. The other thing it does is as data points get further away from the center, the more they're going to contribute to the variance, right? So a bigger value here means there's more spread, smaller values means there's less spread. And so if we add in equal increments, right, we're not adding to the variance equally, right? It's actually going to increase what we call geometrically because we're squaring it. So let's break this down and actually try to depict what's going on here. So here I have on the axis here, I have 5 observations represented by these 5 points. This vertical line here is the mean. Okay, I add all these values, divide by 5, and this is what I get, something a little less than 100. So let's start with this observation here on the far right. So we're going to take that observation minus the mean. All right, so its contribution to the numerator, because we're going to do this for every value, but we're going to start with this one, is first we're going to take the length of that line. So that's what the blue line represents what's in the parentheses. We're then going to square it. So I can take, okay, well, if that line is that long, well, let me draw a length up there so that now for the first observation in our variance estimate, what we have is an area of a square. Okay. And so what we're going to do that for every observation, right? So then for this one, take that, square it, this one, square. And so we're going to add up the area of all of these squares, and then we're going to divide by 5. And here I just kind of put it up above. This is arbitrary where this orange square is, but I just wanted to show that what the variance is then is really the area of the average of the area of all of these squares, right? And this is technically what we call a population variance. So I used a capital S and a capital N, meaning I'm working with a population. But in practice and in R, so if I do the variance function in R, VAR, it's always going to give me a sample variance. So when we do a sample variance, we actually divide by n minus 1. This is technically called the degrees of freedom. This will come up, and we'll talk about it a little bit more when we get to ANOVA. It comes up a lot in statistics, this notion of degrees of freedom. For now, you can think of it as a penalty because we're working with a um a sample, right? We're a little less sure about the variance. Now it turns out as n gets bigger, the difference between the population variance and and the sample variance is gonna get a lot less. And I could show that real quick, I think here. So if I load the visual stats package, right, and I'm gonna create a vector. So I'm just gonna sample from random normal distribution. We'll talk about distribution soon, but let's say I'm gonna do 1,000 and we'll do standard normal is fine. So there's a variance viz. So if I just do the first 5 elements, what I need to do is say plot um, sample variance is true. And then I'll say plot population, variance equals true. So I get both. Okay. So here, when I'm just taking the first 5 observations, right, we can see that the sample variance is, quite a bit bigger than the population variance. But if I go to say the 500, right, you have to trust me that it is indeed drawing both the green and the orange square here, but you can't quite see it. If I do 50, you could see just a tiny bit. So already at 50, the population and the sample variances are going to be the same. And that's because the difference between n and n minus 1, when we're doing with 5, right, we're dividing by 5, and here we're dividing by 4. That's going to have a bigger impact than dividing by 500 and 499. Okay, so in practice, we're always going to use this, but so it's never quite the average of the area of these squares, but pretty close. All right, so let's talk about robust statistics, or the difference between mean and median. So here I just have a random sample of 30 elements, right? It's roughly normal. The mean is 103. The median is 103. The standard deviation is 16.8 in the interquartile range. So that's the 25th to the 75th percentile is 25. Um, Standard deviation and interquartile range aren't really comparable, but mean and median can be, right? They're both measures of center. And so we can represent that here. So here are those 30 observations as black points. The vertical blue line is the mean. The vertical maroon line is the median. And then I have the interquartile range and the standard deviation. Now, what I'm going to do here is add one extreme value. So I'm going to take that vector x of 30 values, which were kind of hovering around 100, with the standard deviation 15. I'm going to add one value here out at 1,000. And here's what happens. So the median went from 103 to 104. And the interquartile range actually went down by a little bit. The mean, however, went from 103 to 132, and the standard deviation went from 16.89 to 161.9, right? So when we talk about robust statistics, we say the median and interquartile range are robust because they are not overly influenced by the presence of outliers. So mean and standard deviation are, and this is going to come up a lot. And when we get to the distributions chapter pretty soon, going to spend some time looking at this and, the how we detect outliers, what are outliers going to do? That's going to be a big thing. But anyways, in terms of reporting, my advice is always just report both mean and median. And if they are the same, that often tells us something. It's not everything, but it can be pretty important. Okay, that summarizes what I said. So we'd already looked at the Lego sets a bit. So I'm just going to kind of move through here, and we're going to get into what we call data wrangling or manipulation. Here, this will link to a cheat sheet if you care. This is the dplyr. So the R for Data Science book is going to, and the Open Interest Statistics book are both going to use dplyr a lot for doing if we need to manipulate our data. So this is kind of a nice little 2-page cheat sheet if you're interested. dplyr is not the only way to do data manipulations. There are three sort of major frameworks. I would say actually there's two. This middle formula syntax. Um, we will use the formula syntax to do modeling, but we're not going to use it for plotting or data manipulation anyway. Technically, it's there, but in the R community, it's rarely used. There's on the left, which is here referred to as the dollar sign syntax. It's often referred to as the base R syntax because this is what's built into the R language. Over here on the right side is the tidyverse syntax, which is largely connected to the dplyr package and some related packages. Um, Now, I've been using R for a very long time before the tidyverse syntax existed. So, on occasion, I will still use the dollar sign syntax because it's so ingrained in what I learned early on. But I do highly recommend learning the tidyverse syntax. When I will occasionally drop in and do it just because it's quick and dirty and it's what I know. However, as I'm going to try to demonstrate, I think it's a little harder to read. So anytime I open an R script that I wrote a while ago and it's using dplyr, I'm always a little happy because I'm going to be able to understand it quicker than the dollar sign syntax. So the example I start with is the sort of prop dot table. I'm actually going to jump over here so we can look at it a little bit more. Excuse me. Uh, um, so we're going to do the Lego sets category. Okay. So, one thing we do I have the pipe operator? I think I'm doing this. Okay. So in R, there are this notion of a pipe. Okay. And this is sort of the foundation for the sort of the tidyverse way of thinking about data manipulation. So there's this percent greater than percent, which is the original pipe introduced in a package called magrittr. But in version of 4.1 of R actually created a built-in pipe, which is this vertical greater than. For 95% of situations, they are interchangeable. On occasion, there's a few things that the magrittr pipe does that the base R pipe can't. But to be honest, I almost always use this one. But let me explain what's going on, right? So contingency tables is a classic descriptive stat um, for doing, to get counts. And so if we say that, so if I say table, Lego sets, category, right? It gives me, how many observations in that data set appear in each of those ones. Now, that's great. That gives me the counts. But really, what I want are proportions. So there's a function called prop.table, and this is how I used to have to do it, right? In base R. So now I'm reading from the inside out. So I'm taking the Lego sets category. I'm going to pass it to the table function, and then the output of the table function gets passed to the prop.table, right? And so if I run that, right, so great, I get the proportions, and this is really helpful because I can see normal sets count for 67.7%. All right, so that's the base R. But if we go to, but really what I want to do is I'm going to take the category variable. I could pass that to the table function, right? And so that gives me the same thing up there. So essentially what the pipe is going to do is take the output from the left-hand side and pass it as the first parameter to the function on the right-hand side. So now I can chain these things together like so. And for me, this is way easier to read because I just read left to right. Okay, I'm taking the category, I'm calling table, I'm calling prop.table. And what's kind of really neat here is the print function is essentially a pass through. So if I want to get both the counts and the proportions, I can just throw a print table in the middle, right? And everything kind of moves along. So pipes take the output from the left, pass it as a first parameter to the function on the right hand side. And so from there, that's kind of how we're going to build this stuff up. So the dplyr has a whole bunch of what are often referred to as verbs, right? You're going to do things to data. So the first thing you might want to do is filter, right? And so the first parameter of the filter function is your data frame. And then from there is going to be your operators. So in this example here, we're looking at otters, a data frame with 4 observations of otters. What we're going to say is type, or I was going to have like our variable name equals equal, or, some logical operator, some value, or what we're testing it against. So in this case, we're saying, well, I want the type equals otter. So we're looking at this. So here's the type column. So we're just gonna eliminate row two because that type is not otter. But then we have this other logical operator. Ampersand is and we want to say site equals bay. Okay, great. So of the ones remaining, okay, that's good. I'm going to keep that. We already eliminated that row. That's good. This row three is good, but okay, this was otter, but the site is wharf. So we're going to eliminate that. Right. And so that's kind of what the filter is doing. I want to eliminate rows based upon some conditions. This um, lists all of the available logical operators that are in R. So the explanation point is just you could just read it as the not operator. It's just going to negate something. So if I write true, great. If I write explanation true, I get false, right? I'm just negating that. Equals equals, two equal signs is testing whether or not A and B are equal. So, right, I could say A equals B. Nope. But A equals A is true, right? We're just doing a simple combination. Not equal, right? So if I go back up and say, change that to explanation, right? Is A is not equal to B. Yeah, that's true. We have greater than equal, less than equal. And then we have this percent in percent. This is a really convenient thing and worth learning because it kind of can help in a lot of ways. So in R, there's a vector called letters that it just gives me the alphabet. And say, for some reason, I want to know where in the alphabet are the vowels. So I could say, I'm going to create a vector called vowels, which is going to be A, E, I, O, and U. Okay. And so what I can do is say, uh, vowel, I'm sorry, it would be letters percent in percent vowels. Okay, so what's happening here is we're going through and it's going to say for each element in the letters, it's going to say, is A in this vector? Yes. Is B? Nope. C? Nope. D? Nope. E is. Okay, all the way through. So it's like saying, is, you know, A equal to A, E, I, or, it's like a big or statement, right? And so from here, what's convenient, right? So the percent in percent is always going to return a logical vector, right? So the length of this, right, is 26. The length of letters, right? There's 26 letters in the alphabet, right? So now I can say, take this and I can pass this to the which command. So what which is going to do is say, well, what position in this logical vector have true values? So the vowels appear at positions 1, 5, 9, 15, and 21. Silly question, but this comes up quite a lot where you might, particularly when you're doing filtering. In terms of like the logical operators, right? This part right here where we're combining things, we have a vertical line, the pipe operator is read as or, and the ampersand is and, right? And these are just simple logical operators. All right, so here's an example. So from our Lego sets data set, right? So if I want to take the, Lego sets and I want to just get the rows where I want educational sets released after 2015, right? And then on these slides, I have here the base R version, which are here mostly to convince you that it's worth learning the dplyr approach. Because in the base R, I have to, in each case, I have to say Lego sets $ theme group. So what the $ is doing here is saying, give me that variable from that data frame. So the result of this is a vector. Okay. And so they both give me the same answer. Select is essentially just returning a subset of columns, right? So here I'm saying, so the Lego sets has 36-ish columns, I think, but I'm only going to work with like 6 of them, right? So a lot of times I want to just remove columns while I'm working with them, so it's a little easier to work with. So that's how I do it in the dplyr way. in the base R, I have to use this square bracket notation. And so the way that works is it's always rows, comma, columns. So I have nothing before the comma because I want to return all rows. And then I have to create this vector of a character vector of the columns I want to get, right? And both give you the same answer. I tend to prefer the dplyr. I think it's a little easier. Relocate allows you to move variables around. In the base R, you're essentially doing the same thing as the select, except now you got to do it in the other OR. But in dplyr, you could say, I want to put all the numeric columns at the end, right? And so that's an easy way to do that. To be honest, you're probably not going to use it too much in this course. I only ever use it when I'm building reports and I want to make sure the columns are in a certain order. I want to group things together. Rename, super super useful, right? So in my example, the variable in my data frame as it comes in is us underscore retail price. That's a lot of things to type, a lot of characters. I just prefer to just have USD, right? US dollar. And so rename is simply new name equals old name, right? And it does it pretty well. Base R, you gotta use the names function, which returns the names of the columns, which is fine, but then you have to change it by position. So my advice is don't even do this because if you read the data frame in and the positions change, then you might rename a column, the wrong column. So rename. This is a good one to know. Okay, mutate. This is how we can create new variables. So here, the first thing I'm going to do is um, I'm filtering out rows where, okay, is NA, if I haven't already said this, this returns true if that value is missing. So NA is how R represents missing values. But notice I'm putting the explanation. So what this is going to do is say, give me all the pieces where all the rows where the number of pieces is not missing and the retail price is not missing. Why? Because I want to create a new variable called price per piece, right? And price per piece is simply the US retail price divided by pieces. So if I didn't do this, I mean, R would still try to do it, but I'd probably end up with a lot of missing values. The result would be missing. But there would be a problem here because I can't divide by zero. And then there are a lot of situations where the pieces is zero. So you can see it just created a new column right on the fly for me. And then the base R approach. You can see I do this crazy subsetting where I'm subsetting the rows. Note on the left side of the column because I'm manipulating the rows. And then I have to use this dollar sign everywhere. Find this a little easier to read. But okay, from here, we might want to do summarizing. So first thing you got to do with the summarize is you got to group or do a group by. So if you've done SQL, this may seem a little bit familiar, but here, I want to do theme groups. I want to summarize my observations by theme group. So I say, okay, that's what I'm going to group by. And then in the summarize function, it looks kind of like mutate. I'm creating new variables, but on the right-hand side, right, I'm saying, well, I want the mean price, which is the mean of US retail price. And by having this group by, I'm getting the mean price for each cat or theme group that we have. And I have my standard deviation, median, n, and missing. So this is a great way to kind of summarize your data by some group. As an aside, I will use quite a lot a function in the psych package called describe. I don't use describe too often, but describe by I certainly use a lot. It does use the notation, right? So what am I summarizing retail price and I'm grouping it by availabilities, right? So it's, oh, I should have done theme group to be consistent. Um, there are a few other parameters here. MAT just says return it in matrix format versus list format. I wish this was the default, but it's not. We're not going to talk about skewness right now. I just told it not to bother giving me that because it wouldn't fit on the slide. But why I like this is it gives me n, the mean, the standard deviation, min, median, max, range, and standard error right off the bat. So this is really, really useful function for me because typically this is everything I want to look at if I'm describing the data set. All right. I know this was a lot. I kind of went through it kind of quickly. But the R for Data Science book, right? You're in the wrangling chapter that and you're going to work on that. I think that's a great resource. The dplyr has a fantastic website, good reference. There's a nice tutorial if you want to see with a different data set. Allison Hirst has this nice tutorial you can go through working with the penguins data set. It's called Palmer's Penguins, really nice data set. And that cheat sheet I talked about before. So I'll entertain any questions, Toki, that you have. Otherwise, you guys can ask always on Slack. And I put the link to the 1 minute paper in there. So everyone and those who are watching it later, please do that when you're done, if you got to this point.
I think, Professor, I think you have explained everything very well. I don't have any question at the moment. If I do come across any question, I'll try to send you an email or maybe like message you on the Slack.
Of course. Of course. Please do. All right, then. Well, then have a great week and we'll see you next week.
You too, Professor. Thank you so much for answering all my questions.
Of course. Anytime. My pleasure. Have a good night.
Wonderful. You too. Thank you,
Bye.
Professor.